This is lecture number 2 for IE 3340 Operation Research. And the lecture for today is on graphical solution to linear programming or LP problems. So in this lecture, we are gonna get started with the formulation of problems. So in this video, we're gonna focus on how to formulate what are the things that we have to have in the model when we formulate it mathematically. We're gonna talk about decision variables, constraints, and objective functions. And we're gonna present an example of how to formulate a problem, a linear programming problem. And then on the next video, we are gonna look at a way of solving these linear programming models. And that's where we're gonna talk about the graphical solution to LP problems. So there's gonna be 2 videos for these lectures. On this video, we're gonna first focus on formulating the problem. So the agenda for this lecture, we're gonna start answering this question: what is a linear programming problem? And as part of this lecture, lecture number 2, we are going to discuss what is the feasible region and what is an optimal solution. And as I mentioned already, then we're going to transition of how to solve a linear programming problem that has only 2 decision variables. So we can apply what is known as the graphical solution to find a solution for such problems. And then we are going to talk about special cases. So using this graphical solution method, how can we identify alternative or multiple optimal solutions? How can we identify when a problem is infeasible? And how can we identify when a problem is unbound? The learning objectives for this lecture is to describe the general characteristics shared by all linear programming problems, and also to learn how to solve graphically those linear programming problems that involve only 2 decision variables. So let's start with answering this question: what is a linear programming LP problem? And we are gonna illustrate this. We're gonna try to answer that question by solving this example. Okay, so what we are trying to do when we formulate problems or linear programming problems, first we are starting with the assumption that we are gonna be dealing with linear equations. Okay, and we discuss in our linear algebra review what linear equations are. So our formulation, our linear programming problems are going to be formulated on that assumption that we're going to have linear equations, and we're going to use this set of linear equations to try to bound the solution space for our problem, meaning that we're going to have a set of constraints that are going to tell us, okay, you can do up to here. And you cannot spend more than this, or you cannot use much of this material because we have a limit. So we're gonna set up all these constraints. We're gonna set up also a group of decision variables that are going to try to answer the questions that we have. Like, for example, how many units of a product we need to produce, or how many units of a product we can produce based on the materials that we have on hand. If we have multiple products, which product should we focus on in a way that we can maximize our profit, for instance? So that's the type of problem that we are going to formulate here with this simple example. We have a manufacturer that produces wooden soldiers and trains. So this is a manufacturer of wooden toys. He has, or she has two products, soldiers and trains. And for each product, there's a description. We have some information about each product. So for the soldiers, We can sell those for $27. And we know that in order to produce those, we need to spend $10 worth of raw materials. Then we also have some information about how much it costs to produce. So the labor is $14 per soldier. And we know that it requires 2 hours of finishing labor and 1 hour of carpentry labor. And then for each train built, they sell for $21. They use $9 worth of raw materials. Building this or producing these trains increased Yapeto's variable labor overhead by $10. And they require 1 hour of finishing labor and 1 hour of carpentry labor. These are the assumptions for the problem. Each week, Yapeto can obtain all needed raw material. So there's not a limit in terms of the raw materials. We have as much material as we need. However, there's a couple of limitations here in terms of the hours of staff hours that we have in this company. There's only 100 finishing hours available, and there's only 80 carpentry hours available. Also, we have, in terms of the demand, the demand for the trains is unlimited. So we can sell as many as we build. However, for the soldiers, at most 40 soldiers are bought each week. So if we plan for the next week, we don't want to produce more than 40 soldiers because those are not gonna sell. So our goal or our problem is to maximize the weekly profit, which is the difference between revenues and expenses. But that's what we want to answer. We want to find out, okay, how many products of each type we should produce this week so we maximize our profit given the information that we just discussed. So the Yapeto solution model incorporates the characteristics shared by all linear programming problems. So each linear programming problem will have 3 parts. The first part, which is usually what we try to define first, those are called the decision variables. And they describe the decisions to be made. So for example, what are the questions that you want to answer using the model? So in this problem, we have 2 questions. We want to know, and we can describe those 2 questions or those 2 unanswered questions using decision variables. So I'm gonna use X1, which is the number or the first unanswered question, the number of soldiers produced each week. I don't know how many soldiers should I produce this week. So in this case, I'm using an index I that has a set of 2 items in it. And 1 is gonna be used to model the, so when I equals 1, I'm referring to soldiers. And when I equals 2, this means that I'm referring to the trains. So X1 is the number of soldiers produced each week. I don't know what that is. I want the model to tell me based on the information that I'm providing. And X2 is the number of trains produced each week. which I don't know. Okay, so these are two things that I want the model to answer. I want to give the model all this information that we just discussed, and I want the model to tell me, okay, X1 is this much, X2 is this much. The second part of a linear programming model is what is called the objective function. In any linear programming model, the decision maker wants to, one of these two, wants to maximize something or minimize something. So when we are maximizing, usually what we want to maximize something related to the revenue or the profit. When we look at minimization, we are usually minimizing the cost. And these two, the objective function is always in terms of maximizing something or minimizing something. And these are functions that are used in the decision variables. Okay, so we are going to define a function that uses the decision variables and is going to try to maximize or minimize that function that includes these decision variables. This function to maximize or minimize is called the objective function. The third part, well, in this case, we're still talking about the objective function. So for the Yapetto weekly profit, we can express this in terms of the decision variables, X1 and X2. So we can formulate a function that can describe the profit of this company using these decision variables. So the weekly profit is going to be defined in terms of the weekly revenue minus the weekly cost of the raw material minus the cost or the weekly variable cost. So anything we sell, the summation of all our sales, that is the profit. Then we're gonna take the costs associated with building them and also the weekly variable costs in terms of the labor. We subtract those two amounts and then that's our profit. So the weekly revenue is again stated in terms of our sales. So we know that each soldier is sold for $27. And we can sum also the trains are sold for $21. Right? So we can multiply that revenue by the decision variable. So if I sell 2 soldiers, then that means that my profit is 2 times 27. If I sell 1 train, then my profit is $21. I'm sorry, my revenue is $21. So now in order to get the revenue, I need to subtract the cost. In order to get the profit, I need to subtract the cost. So I have a cost associated with the raw materials, and that cost is, I stated on the previous slide, is $10 for soldiers, and it is $9 for the trains. And then there's also a variable cost associated with the soldiers. So that's $14 times X1 plus $10 for the trains, X2. So if I sell 100 trains, then I had to multiply that by 21 in order to get the revenue. And then I had to multiply 9 times 100 to get the material cost. And then I had to multiply 10 times 100 to get the weekly variable cost. The difference between the revenue and the material and variable cost is what's going to give me the profit. So in this case, that's going to be equal to 27x1 plus 21x2 minus 10 times x1 plus 9x2 minus 14x1 plus 10x2. And after solving this equation, I get the function 3x1 plus 2x2. So at the end, this is my function, 3x1 plus 2x2. So every time I sell a soldier, I earn $3. Every time I sell a train, I earn $2. Thus, the Yapeto's objective is to choose x1 and x2 to maximize this function 3x1 plus 2x2. We use the variable z to denote the objective function value of any linear programming model. The Yapeto's objective function is then the maximization of z, where z is 3x1 plus 2x2. Maximize will be abbreviated by using max, and minimize will be abbreviated by using min. Okay, so we have the first two parts. One extra comment is that we know that as x1 and x2 increase, the objective function grows larger. So for Yapeto, the values of x1 and x2 are limited by the following three restrictions, which is our third part for the model. We have already defined the first part, which is the decision variables. Second part is the objective function. And now the third part is to define the constraints. In this problem, we have three constraints. We know that each week, no more than 100 hours of finishing time may be used. Constraint number two is each week, no more than 80 hours of carpentry time may be used. And because of limited demand, at most 40 soldiers should be produced. So these three constraints can be expressed mathematically by the following equations. Equation number one, or constraint number one, is a linear equation. We know that in terms of finishing time, the soldiers requires 2 hours. So each soldier will require 2 hours. And each train is gonna require only 1 hour. And we know that the summation of those two has to be less than or equal to 100, which is what we have available. Constraint number two is in terms of carpentry time. And we know that both of the products require 1 hour. So it's gonna be 1x1 plus 1x2. Let me fix that. So on. Has to be less than or equal to 80. And then finally, we have the constraint for the limited demand of the soldiers. So we know that that has to be less than or equal to 40. We should not produce more than that. And since the decision variable for soldiers is x1, x1 has to be less than or equal to 40. The coefficients of the constraints are often called the technological coefficients. The number on the right-hand side of the constraint is called the constraint's right-hand side. Design restrictions. To compute the formulation of a linear programming problem, the following question must be answered for each decision variable. Can the decision variable only assume non-negative values, or is the decision variable allowed to assume both positive and negative values? If the decision variable can assume only non-negative values, the sign restriction xj greater or equal to 0 is added. So in our case, we don't want to produce negative 10 soldiers or negative 10 trains. So we have a non-negativity or non-negative constraint. for both decision variables. We have to make sure that those are greater or equal to 0. So if the variable can assume both positive and negative values, the decision variable xi is unrestricted in sign, which is not the case for this problem. So combining the sign restrictions, x1 has to be greater or equal to 0, and x2 has to be greater or equal to 0, with the objective function and constraints, yields the following optimization model. So this is the optimization model for the Gepetto problem. We want to maximize our profit. That's our objective function. And the profit is given by 3x1 plus 2x2. And that has to be subject to all these constraints that we just discussed, plus the constraints for the sign restrictions. So we want to make sure that x1 is a positive number. We want to produce 0 or a positive number, and x2 the same. Okay, so this is the problem, the Gepetto problem. And now we're going to talk a little bit more about the concepts of a linear function and linear inequality. So to tie what we did today with what we discussed in terms of linear algebra. So the concept of linear function and linear inequality. A linear function is a function f, a function of x, where of x1, x2, xn is a linear function if and only if, for some set of constraints, a set of constants c1, c2, up to cn, the function evaluated in terms of x1, x2, up to xn is equal to the coefficients c1 times x1 plus coefficient 2 times x2 up to cn up times xn. So it is a linear function even only if the sum for some set of constants when we evaluate that function in terms of x, it's going to be equal to the summation of those coefficients times the decision variables, the summation of those. So for example, if we have a function in terms of x1 and x2 equals to 2x1 plus x2, it's a linear function of x1 and x2, but if we have a function in terms of x1 and x2 equal to x1 squared times x2, this is not a linear function of x1 and x2 because we have a multiplication and we have a coefficient square of x1. So thus, that is not a linear function. For any linear function f of x1, x2 up to xn, and any number b, the inequalities f of x1 up to xn less than or equal to b, and f of x1, x2 up to xn greater or equal to b are linear inequalities. A linear programming problem, LP, is an optimization problem for which we do the following. We attempt to maximize or minimize a linear function called the objective function of the decision variables. The values of the decision variables must satisfy a set of constraints, and each constraint must be a linear equation or inequality. A sign restriction is associated with each variable. For each variable xi, the sign restriction specifies either that xi must be non-negative, or xi greater or equal to 0, or that xi may be unrestricted in sign. In terms of proportionality and additive assumptions, the fact that the objective function for an LP must be a linear function of the decision variables has two important implications. The contribution of the objective function from each decision variable is proportional to the value of the decision variable. For example, the contribution to the objective function for 4 soldiers is exactly 4 times the contribution of 1 soldier. Number two, the contribution to the objective function for any variable is independent of the other decision variables. So no matter what, for example, no matter what the value of X2, the manufacturer of X1 soldiers will always contribute 3 times X1 dollars to the objective function. So decision variable 2 has no impact on how much X1 is going to contribute to the model. The fact that each LP constraint must be a linear inequality or linear equation has two implications. The contribution of each variable to the left-hand side of each constraint is proportional to the value of the variable. For example, take exactly 3 times as many finishing hours to manufacture 3 soldiers as it does 1 soldier. Number two, the contribution of a variable to the left-hand side of each constraint is independent of the values of the variable. For example, no matter what the value of X1, the manufacturer of X2 trains uses X2 finishing hours and X2 carpentry hours. The divisibility assumption. The divisibility assumption requires that each decision variable be permitted to assume fractional values. For example, this assumption implies it is acceptable to produce a fractional number of trains. The Gepetto LP does not satisfy the divisibility assumption since a fractional soldier or train cannot be produced. The use of integer programming methods necessary to address the solution to this problem will be discussed later in this course. The certainty assumption. The certainty assumption is that each parameter, the objective function coefficient, the right-hand side, and the technological coefficients are known with certainty. The feasible region and optimal solution. The feasible region of an LP is the set of all points satisfying all the LP's constraints and sign restrictions. So for instance, X1 equals 40 and X2 equals 20 is in the feasible region since they satisfy all the constraints in this problem. X1 equals 15 and X2 equals 70 is not in the feasible region because this point does not satisfy the carpentry constraint. If you substitute that information into the carpentry constraint, you'll see that 15 plus 70 is greater than 80. So those values does not satisfy that constraint. So that those values are not part of the feasible region. For a maximization problem, an optimal solution is a point in the feasible region with the largest objective function value. For a minimization problem, an optimal solution is a point in the feasible region with the smallest objective function value. Most of LPs have one optimal solution. However, some LPs might have no optimal solution or an infinite number of solutions. The optimal solution to the Gepetto LP is X1 equals 20 and X2 equals 60. This solution yields an objective function value of X1 times 3 plus X2 times 60. So in this case, Z equals 3x1 plus 2x2. So if we substitute those numbers here, is 3 times 20 plus 2 times 60. That is going to be equal to $180. How do we get to this solution? That's what we're going to discuss in the next video. When we say that X1 equals 20 and X2 equals 60 is the optimal solution, what we are saying is that no point in the feasible region has an objective function value or profit exceeding $180. Okay, so on our next lecture, in the next video lecture, we are going to discuss how to solve a two-decision variable LP problem. and we're going to use the Gepetto problem as an example, using the graphical solution method. We have a lab for this lecture, so you can work in the lab now. The lab is going to ask you to formulate a problem. So I'm going to provide you with a description of a problem, and I want you to go and formulate the decision variables, the objective function, and to do your best effort to define the constraints. Okay, so that's on the modules. So please go and work with that lab.